Hello, in this video we are going to go over the solution of the problem 993, cousins in a binary tree. Two nodes of a binary tree are cousins if they have the same depths but have different parents. For example, here I have node 8 and 4. These two nodes are cousins because they are both at height 2 but they have different parents. But node 4 and node 7, they are siblings, they are not cousins because they have same parents. Or we could say node 5 and node 7, they are not cousins because they are not even at the same height. Okay, we are going to write a function called isCousin, and this function is going to get three inputs. The first input is the root, which is the root of the tree, and then I have x and y. There are two nodes that we are going to check. Okay, we are going to solve this problem in this way. I'm going to define a dictionary, and keys of this dictionary are the node values. And for the values of the dictionary, I'm going to use a tuple. The first element of the tuple will be the height of that node, and the second element of the tuple will be the node parent value. That's the value of its parent. If I have that dictionary for all of the nodes of the tree, I can run a simple comparison and say if dictionary X first element, which is the height, is same as dictionary Y first element, which means that node X and Y are at the same height, and dictionary of X1 is not equal to dictionary of Y1, which means that they don't have the same parents, because this is going to be the value of their parent in the second element of the tuple. If both of them are correct, means that X and Y are cousins because they are at the same height with different parents, and I can return true. If not, I just return false at the end of the function. Now let's go and use BFS to create this dictionary. The first thing that we are going to do is to import DQ from collections. We say from collections import DQ, and then I'm going to initialize a variable called DQ, and I'm going to initialize Q like this. I'm going to put the root inside the Q. Also, for the second element of the tuple, I'm just gonna put none. Now I can start the while loop. I say while Q. Now I'm going to go forward and visit all of the nodes in each height. We say for I in range of length of Q. Then we are going to pop left from the Q and say node parent value equals Q dot pop left. Okay, and now you can see that for the first one, that was a root because it doesn't have a parent. That's the reason we used none here. Then we are going to go forward and add the neighboring nodes to that, and each node has two neighbors, left and right. We say if node left, which means that node left is not none, we just add that to our queue. We say queue dot append node left and node value. Why node value? Because node value here is the parent of node left. And we say if node dot right queue dot append node dot right and node dot value. Again, node dot value is the value of the parent of node dot right. And inside the for loop, I'm going to create that dictionary. We say dictionary of node dot value equals first element is the height and the second element is the value of the parent. Okay. We also need to define this edge at the beginning, that is 0, and in the while loop that is gonna increment by 1. Say edge plus equals 1. Okay, now we are done with the code. Let's run it, and we could check for 4 and 7. We see for 4 and 7 they are sibling. It should return false. Let's run it. We get false. And if I check, for example, for 8 and 4, I should get true. That's true. Or maybe for 5 and 3 it should give us false because they're sibling. So 5 and 3 is false. Maybe we can check for 1 and 7. They're not at the same height. It should return false. 7 and 1. False. Okay. Now let's talk about time and space complexities. For the time complexity, we are conducting a BFS, and because of that, we are visiting each node only once, and the time complexity is order of n. Our space complexity is also order of n because the queue that we created is gonna be the size less than the 2 times the maximum number of the nodes, which is 2n, because we have 2 values for q, which is order of n. Also for the dictionary, we are recording for each single node 2 information, so it's gonna be 2n. As the result, the space complexity in the big O notation is order of n. Okay, this is the solution of the problem 993, and thank you so much again for watching this video.